Yeah, in my last class we started discussing about the one of the very important topics in power electronics known as the inverters. Input is DC, output is AC. Okay. I am calling output as AC because the average value of the output voltage is 0. It need not be a pure sinusoid. I said it may be very important topic in power electronics, but then till now we are not very much convinced regarding the use of such a equipment, because power that is generated is AC. Here is an equipment which converts DC to AC. I told you that in any DC to AC conversion or DC to AC equipment, power electronic equipment, there has to be a AC to DC converter, okay, which converts input AC to DC, and this DC forms a input to the DC to AC converter. Okay. In the process we found that, or we have seen a equipment wherein input is a 12 volt DC and output is 230 volt 50 hertz AC. Okay. This is nothing but, sometimes we call it as a UPS, uninterrupted power supply, or we also call it as an inverter. Okay. Then we started discussing about the theory of a 3-phase induction machine, and we found that if the machine is driving a constant torque load, the input to the machine remains approximately constant and it is independent of speed of operation. Okay. So as the speed decreases, S times the input is dissipated as heat. So therefore, even for fan type of loads, if you want to vary the speed over a wide range, it is always advantageous to vary the synchronous speed itself. Okay. These observations we had made in the last class. Okay. Then we started discussing about the equivalent circuit of an induction machine, and I told you that if the power rating of the machine is high, or in for high power motors, the values of series parameters, the winding resistance as well as the leakage fluxes, is relatively low. So we can shift the magnetizing branch to the source side, provided the frequency of operation is fairly high. In the sense, if the operating frequency range is around say 30 to 50 hertz or so, you can call, or we can say that E1, the voltage across the magnetizing branch, is approximately equal to the supply voltage itself. Okay. So therefore, see in this equation, magnetizing current is given by E1 divided by 2 pi f into Lm. Actually it is not approximate, this is equal. Im is equal to, please, this is equal to E1 divided by 2 pi f into Lm, which is approximately equal to Vs divided by 2 pi f into Lm. Okay. Where See, this is the equivalent circuit we have discussed, and this is the equation we have derived it. So, we also discussed about one of the possible cases in which we kept Vs constant and we tried to reduce frequency. Since we are decreasing the frequency, synchronous speed will fall. Okay. Vs is held constant, F reduces, therefore the magnetizing current increases. Therefore, the equation says that if the magnetizing current increases, flux also increases. That is what the equation says, but then in the machine we all know that they are operated at the knee point. I mean knee point in the sense the point at which the saturation begins to start. So, Im is no longer linearly varies with flux, or flux does not change linearly with Im. Okay. Machine starts getting saturated, therefore source current will become peaky. So, the moment the source current becomes peaky, harmonics are introduced, power factor also falls, and core loss are going to increase. So, we had concluded that keeping Vs constant, maybe at its rated value, and decreasing F is not a solution. Okay. So, what could be the second option? Second option is we will keep Vs constant at its rated value, okay, and increase F above the rated. Okay. In the previous case what we did, we kept Vs constant and tried to reduce the frequency below the rated. Not possible. The second case, we will keep Vs constant at its rated value and we will try to increase F to increase Ns. What the equation says? Im is given by Vs divided by 2 pi f into Lm. Vs constant, F increases, therefore Im reduces. If Im reduces, flux also reduces. Okay. Maybe this linear, the relationship between Im and phi will be approximately linear, because beyond the knee point is non-linear, below the knee point relationship between BH curve is almost linear. See, for all practical purposes, even a 3-phase induction motor is a constant speed motor, because reduction in speed with load is not much. Say for example, for a good induction machine, no load speed for a 4-pole 50 hertz motor, no load speed could be of the order of 1485 rpm or so. Synchronous speed is 120 f by p, it is 1500 rpm, f is 50, p is 4. So, NR at no load could be of the order of 1485, and on full load it could be of the order of 1460 or so. So, reduction in speed from full load to reduction in speed from no load to full load is of the order of say 20 to 25 rpm, okay, and the base value is 1500 rpm, the synchronous speed. Therefore, for all practical purposes, induction motor is also considered to be a constant speed motor. Okay. Coming back to this theory, I said V is kept at V rated. I am increasing the frequency above the rated. Therefore, synchronous speed, which is approximately equal to or maybe slightly higher than the speed of rotation of the motor also increases above the rated. In other words, machine is now running at a speed which is higher than the rated. Air gap flux has reduced because Im has reduced. Im is equal to Vs divided by 2 pi f into Lm. Flux has reduced and speed of rotation has increased. Now let me recall a theory on DC machines. What did we do to increase the speed above the rated? We kept the armature voltage constant, okay, and we will try to reduce the flux by reducing the voltage applied to the field winding, and we called it as a field weakening mode of operation. See, in DC motor speed control, separately excited DC motor speed control, armature voltage is held constant and we try to reduce the flux by reducing the voltage applied to the field winding, and we call this mode of operation as field weakening mode. Since speed is inversely proportional to flux, speed started increasing above the rated. The same operation is taking place in this case. Speed of rotation is above the rated and air gap flux is falling. Okay. So this mode of operation is similar to field weakening mode of DC machine. Okay. We may not be directly changing the voltage applied to the field. Of course, here Xm, those points are not available outside, whereas in DC motor we could have independent control of the flux. Okay. So I can make another conclusion, that is a DC to AC converter should be able to provide a constant voltage and the frequency should be able to increase. Okay. I will repeat, magnitude of output voltage should be held constant, I should be able to keep it constant, and we should be able to increase the frequency above the rated. We do not want to keep the voltage constant and decrease the frequency, that operation is ruled out, but we should be able to keep the voltage constant and to increase the frequency to increase the speed of rotation. Okay. So this is another feature a DC to AC converter should have. Now let me take you to the third case. What did we do in the first case? We kept V constant, tried to reduce F. In the second case, we kept V constant and increased the frequency. Yes, it is one of the possible modes of operation. Now what we will do is, we will keep V and F constant. In other words, we will try to reduce V as well as F. Okay. See in this equation, Im is proportional to flux, and this is approximately equal to V, the supply voltage. Maybe in the previous equivalent circuit I must have called it a Vs, okay, divided by 2 pi f into Lm. Okay. So if I keep V by F constant, the flux will remain constant. Okay, flux will remain constant. Okay. Of course, you may say that increase V above the rated. It is not a good engineering practice. The maximum voltage that I can apply to the machine is its rated. Okay. So you can apply a reduced voltage to the motor. That's what I said, we will keep V by F constant and we will try to reduce V in such a way that V by F ratio remains constant. Okay. So as F reduces, 120 F by P, which is nothing but the synchronous speed, also reduces. Okay. Therefore, another feature of a DC to AC converter is that it is possible to keep V by F ratio constant till the rated. So from low speed of operation, I am calling low speed, why I will tell you later. From low speed of operation or from low frequency to 50 hertz, which is the rated frequency, it should be able to keep V by F ratio constant. Okay. In other words, V by F relationship should be linear. Okay. So this mode is similar to constant torque of operation in DC motor. Or how do we reduce the speed of operation of DC machine? We are kept IF constant. Okay, we are kept IF constant and we try to reduce the armature voltage. Omega is directly proportional to the applied voltage to the armature. So we are kept flux constant and we will try to reduce the armature voltage, therefore speed reduce. Same thing is happening even here. I will keep V by F constant, flux remains constant. F reduces, therefore Ns, the synchronous speed, reduces. Nr should be less than Ns, so Nr also reduces. Same operation, the constant flux operation in a DC machine, which is similar to this operation in inverter fed induction machine. Okay. By the way, why did I say that low frequency? Why not zero frequency or 0.1 hertz or 0.2 hertz? Why did I say from low frequency to 50 hertz V by F relationship is linear? Why not down to very low frequency? Now I will take back to the equivalent circuit for induction machine. See, I have just drawn the stator side, I have not shown you the rotor side, and I have not shown you, or in this circuit leakage reactance is missing. Why it is missing? It is very much there. Why it is missing? I said frequency has reduced, frequency of operation has reduced. Okay. At 50 hertz rated frequency itself, the values of these series parameters, winding resistance, leakage reactance, I said they are low at 50 hertz. Now at low frequency, say around 10 hertz or so, the value of XL has reduced to 0.2, corresponds to its rated. So at 50 hertz it is low. Now the frequency of operation say around 10 hertz or 5 hertz, there is a proportionate decrease in the magnitude of XSL. Okay. So I can safely neglect the leakage reactance. Okay. I said frequency of operation has come down. Frequency of operation has come down here in this of the circuit. It could be of the order of 5 hertz, 2 hertz or 3 hertz or whatever. When I am saying it is a low frequency AC, I can use a direct DC circuit analysis here. Say 2 hertz is nothing but a DC itself. Please try to understand. A 2 hertz AC, I can safely say it is nothing but DC. Okay. So I can directly write here magnitudes. I don't need to take phasors into account. V is equal to E plus Is into R. Okay. So I can directly add the magnitudes. If it is an AC circuit analysis, I need to use phasors. Okay. The moment I use phasor addition, if the power factor is lagging, then I can say that B is approximately equal to E for low values of RS. Now, but then if I am using directly, if I am adding directly the magnitudes, okay, now it may so happen that there will be a significant difference in the magnitude of E and V. Okay. Now see, E is V minus Is into R, direct magnitude subtraction, direct subtraction. So what is to be done is, or what is done is, at low frequency you need to compensate for IS-RS drop. You need to compensate for IS-RS drop. In other words, this is no longer linear. Okay. That's why I have shown you as dotted. Actually, it is a curve starting from here. It is like this. Anyway, that this generally should be discussed in drives, but just you may be a bit curious to know why it is not linear till the origin, so I just discussed. Okay, it is a non-linear function at low frequencies. Okay. Anyway, so these are the conclusions that I can make. A DC to AC converter should have another feature. That feature is till the base speed, or from very low speed to the rated speed, both magnitude of the voltage as well as the frequency should be variable. Okay. So that maybe V by F remains constant. Okay. So therefore, a DC to AC inverter or converter should have two features. One is, it should be a variable voltage, variable frequency source. Remember, it should be a variable voltage, variable frequency source till the base speed, from 0 to base speed, and from above the base speed, constant magnitude of voltage and frequency should be able to vary, or it should be able to vary the frequency of operation above the base speed, keeping the magnitude of voltage constant. So these are the two important features a DC to AC converter should have, or the DC to AC converter used in drives or AC drives, or DC to AC converter used to vary the speed of rotation of AC machines. A very important applications. Let me tell you one thing, majority of DC to AC converters or majority of inverters are used in AC drives. They are used to vary the speed of rotation of the induction machine. Okay, majority. And remaining significant application is UPS, uninterrupted power supplies. And another application is high frequency induction heating. High frequency induction heating. Okay, we'll see some time later. So we have discussed the need for DC to AC converter. Having discussed this, now I will start discussing about the various ways to get AC supply from DC supply. Okay. Basically, there are two types of inverters. The first one is, if the input to the inverter is held constant, input voltage is held constant. So I will repeat, if the input voltage to the inverter is held constant, in other words, input to the inverter is a voltage source, we call it as a voltage source inverter. See in this figure. So this is the inverter, input is, I marked it as a voltage source or a battery. Okay. So the moment I say it's a battery, I can represent as a voltage source, almost as a ideal voltage source. Magnitude of voltage is independent of the current that is supplying. Okay. So in other words, the input impedance or the Thevenin impedance is very small. The Thevenin impedance of a voltage source inverter is very small, any voltage source. So therefore, you should be extremely careful in operating this inverter. So I will repeat, Thevenin's impedance is very small. Okay, Thevenin impedance is very small. Input is a voltage source, therefore voltage cannot reverse, or polarity of this voltage source cannot reverse. Okay, but then current should be able to reverse, remember. Okay. So a voltage source can supply or sink any amount of current. So even in a VSI inverter, voltage source inverter, in a VSI, current should be able to reverse, or current does reverse in a VSI. Okay, current does reverse in a VSI. Voltage polarities cannot reverse here. Okay, I have shown here 3 lines indicating a 3-phase inverter. You can have a single phase inverter also. I said input is a voltage source. I can have a current source also. Okay, so I have a variable DC here, source, and a large inductor is connected in series to the inverter. So a voltage source in series with a large inductor can be represented by a current source. See, this we did in DC to DC conversion. I said input stage of a Chuk converter, we had a voltage source and an inductor. So I said we can represent that combination by a current source. Okay, so it could be represented by almost ideal current source. Since there is a large inductor here, current cannot change its direction. Current cannot change the direction here. Okay, but that we know that voltage across a current source can be either positive or negative. Just the opposite in a VSI, voltage source inverter. Okay, here current can reverse, not voltage, whereas in a current source inverter, input voltage to the inverter, out here can reverse, but not the current, okay. In other words, input impedance, or if I have to represent by a Thevenin equivalent, I have a current source and a large inductance here, okay. So remember, there are two types. One is a voltage source inverter, current can reverse and not the voltage, and we have a current source inverter, this voltage can reverse, input voltage to the inverter can reverse and not the current, okay. The advantages of voltage source inverter over current source inverter, or the difference between the voltage source inverter and the current source inverter, we will discuss in detail after discussing the various topologies of VSI as well as the CSI, okay. Yeah, now we will discuss the various circuit configuration of a voltage source inverter, VSI. Yeah, a half bridge configuration, half bridge is a basic building block, okay. We have a center tapped DC source, VDC by 2, okay. Two switches, S1 and S2, and load is connected between the center point of the voltage source and the center point of these two devices, okay. I will just repeat, I might have done this in AC to DC conversion. When I represent a switch in this fashion, when I close the switch, current flows in this fashion, okay. Current flows in this fashion. Voltage source inverter, VSI, polarities of input voltage source cannot reverse, current should be able to reverse, okay. So therefore, there is a switch here. If I close this, current flows in this direction, okay. Current should be able to reverse, current should be able to flow into the source now, back into the source. So I need to connect a anti-parallel diode across the switch, okay, a D1, okay, across S1, similarly D2 across S2, okay. So positive current, if I term this as a positive current, the switch carries, a negative current diode carries. I said you need to connect an external diode across S1. In fact, all the semiconductor devices, say for that matter IGBT, BJT, they do have internal diode connected across. So you do not need to connect a separate diode across the switch. If you I said voltage is always positive, polarities cannot reverse, current can reverse, positive current, negative current. So in a VI plane, operation is on two quadrants, okay, positive voltage, positive current and negative current. So therefore a VSI, a voltage source inverter, is also known as a two quadrant converter, okay. Two quadrant, voltage positive, current could be positive or negative. Okay. What is another feature of VSI? The switching signals for S1 and S2 they are always complementary. Okay, S1 and S2 are complementary. Okay, so if S1 is on, S2 should be off. S2 should be off. Okay. So how does this circuit work? S1 is on for T/2 period, S1 is turned off and S2 is turned on for the remaining T/2 period. Okay. So when S1 is on, what is the equivalent circuit? Okay. See in this figure, when S1 is on, point A gets connected to the positive of the battery. Okay. Point A gets connected to positive of the battery. So this is the equivalent circuit. Voltage applied to the load is positive VDC by 2, because with respect to B, point A is at higher potential. Okay. Let us assume that load is RL. Okay. So equation for I is P by R into 1 minus e to the power t by tau. Okay. So therefore for the first cycle t is equal to 0. Okay, current starts from 0, increases linearly and becomes exponential depending upon tau and t. Okay. It reaches some value, and at this point T/2 you open the switch S1 and close S2. Okay. So when you close S2, this is the equivalent circuit. Okay. See in this, when I open S1, close S2, point A gets connected to negative of the battery. Okay. So in other words, point B is at a higher potential compared to point A. Okay. This is the equivalent circuit. But then when I opening S1 and closing S2, at that time current is finite. Okay. Now the current will decay and it will reverse. So at steady state, if I have to draw the current waveform, it may look like this. So when I am closing S1, okay, current is negative, it increases, becomes positive and attains a positive value. After some time, when you open S1 and close S2, okay, it starts decreasing, becomes 0 and becomes negative, and this cycle repeats. Okay. Now what are the observations that you can make from this waveform? I said S1 is turned on at this point, maybe at NT, N is could be anything. Okay. A positive voltage is applied, but current is negative. From P to Q, current is negative. Voltage applied to the load is positive. Okay. Which device is carrying current now? See here, positive voltage, but then negative current. From P to Q, current is negative. See in this circuit, I can apply positive voltage to the load only when this point is connected to this point. Okay. A positive voltage is applied to the load only point A gets connected to positive of the battery. That can happen when S1 is on or D1 is on. Remember, this point potential of this is same as potential of this when S1 is on or D1 is on. Okay. I have assumed a positive value of current, in the sense positive direction of current is when it is flowing from A to B. Okay. When the current flows from A to B, it is assumed to be positive. But then we found that positive voltage is applied to the load, but then from P to Q current is negative. So in this circuit, current is flowing from B to A, and this point is connected to this point. So it can happen only when D1 is conducting. Okay. So therefore, though you have closed the switch at NT, that switch will not carry current immediately. It all depends on the circuit parameters. Okay. Therefore, from P to Q for RL load, D1 is conducting even though you have closed the switch S1. Okay. So because of this, the gating requirement changes. See, assume that switches are made of thyristors. Okay. Let us assume, because thyristors also, they are controllable devices. So it is possible, in principle, I can use SCRs. And we all know that a sharp pulse will turn on the thyristor. So at steady state NT, I want to trigger T1 or thyristor 1, a sharp pulse is applied, thyristor will not turn on at all. Because current is negative. It is flowing through the diode that is connected in parallel through the device. Okay. Current starts flowing through the device or S only after Q. Say from Q to R, voltage is positive, current is also positive. From Q to R, voltage positive, current positive. So therefore, it can happen only if S1 is carrying the current. Because positive voltage, this point should be connected here, current also flowing in this direction, so S1 is carrying current. So in other words, if S1 is realized by thyristor, you need to have a gate pulse beyond Q. Okay, because gate pulse should be present till the current through the device is higher than the latching. That's what you have been told. Okay. So a gate pulse should be present beyond Q. Okay. Now what happens from R to S? Voltage applied to the load is negative. But then current is positive. See in the circuit, voltage applied to the load is negative. In other words, A should be connected to this point. Current is positive. Current is flowing from A to B. But then this point should be connected here. It can happen only when D2 is conducting. Okay. Because when D2 conducts, potential of this is same as this, but then current is flowing in this fashion. So therefore from R to S, D2 is carrying the current. From S to the end of that cycle, S2 is conducting, because voltage applied is negative, current is also negative. So you can conclude that even though you have turned on the device, if the load is RL, it may not be carrying that current. It may not be carrying the current. Remember, in a VSI, just because the device is turned on, it doesn't mean that the device is carrying the current. It may so happen that the diode that is connected across the device may be carrying the current. Okay. What is another observation that you can make from this operation? Okay. S1 is on for T by 2 and S2 is on for remaining T by 2 duration. So time for which S1 or S2 is on will determine the frequency of the output voltage. I will repeat, the time for which S1 or S2 are on will determine the frequency of the output voltage. So for example, if S1 is on for 10 millisecond and S2 is on for another 10 millisecond, the entire period is 20 millisecond. That is nothing but I have a 50 hertz AC supply. It may be a square wave in this case, but I am calling it AC because average value is 0. Instead, if S1 is on for 50 millisecond and S2 is on for another 50 millisecond, so entire period is 100 millisecond. So you have a 10 hertz AC supply. So therefore, the time for which S1 or S2 are on will determine the frequency of the output voltage. Okay. Now, what is another observation that I can make? I said S1 and S2 are complementary. In other words, switching signals for S1 and S2 are complementary. Basically, it is an ideal situation. Let me tell you one thing, it is an ideal situation. What happens if they are truly complementary? What happens? I said each device has its own time or takes its own time to attain a blocking mode. Okay? Just because a BJT or an IGBT, if you withdraw the gate pulses, it doesn't mean that device has attained a fully blocking mode or device has completely turned off. What may happen is you have withdrawn the gate pulses for S1 and you have applied a gate pulses for S2 simultaneously. And it means both of them conduct, there is going to be a short circuit across the DC bus. See here, S1 was on, you have withdrawn the gate pulse, but then it has not completely turned off, and you have applied T2, it started conducting. Okay, now there is going to be a shoot through. In other words, there is a short circuit here. Okay, there is a short circuit here. Input is the ideal voltage source. Thevenin, the impedance is approximately 0. Okay, so a large current will flow and may damage the devices. Okay, so that's why reason you should be extremely careful in operating a voltage source inverter. Two devices should not be on at any given time. or these two devices should not be on at any given time. In other words, there should be some delay between the gate signals applied to S1 and S2. I will show you in this figure. See here, there is something known as the dead time, Assume that this is for S1 and this is for S2. See, S1 is turned off, okay, and for some time both devices are off. S1 is turned off here, and after some time S2 is turned on. In other words, during this period, both S1 as well as S2 are off. Same thing is true here. Both S1 and S2 are off. See, S2 turned off. After some time, S1 is turned on. Okay. So for some time, both the devices are off. Okay. Now you may think that both the devices are off. Load is RL, inductive circuit. Whether the inductive circuit gets broken or the currents become zero instantaneously? No, answer is no. Then what happens? Both the devices are off. Remember, there is a diode connected across each device. And current cannot change instantaneously in inductor. Okay. So in the circuit, say if S1 is turned on and if the current is flowing from A to B, you opened S1, okay, immediately D2 starts carrying that current. In this circuit. Okay, current was flowing from A to B, you opened it, you close this, current will start from D to A. Okay. So another important point that to be remembered is there should be a delay or there should be a dead time between the gating signals of S1 and S2. In the dead time, none of the devices are on. Okay. A second point that is to be remembered is a voltage source inverter is also known as a two-quadrant inverter. Current can reverse, not the voltage. And third point, having turned on the device, that device may not carrying the current. Okay. The diode which is connected across it may be conducting. Okay. Output voltage waveform is a square wave, and I called it as a DC to AC inverter because average value is 0. We are interested in only in a sinusoidal component whose frequency is equal to the frequency of the square wave itself. Okay. So if I take the harmonic, or if I write a harmonic series or a Fourier series of this, it has all the odd harmonics. It's an odd function, So there is a third harmonic, 5th, 7th, 9th, 11th, including the fundamental. Yeah, this is the fundamental. Okay. If VDC by 2 is the magnitude of the square wave, this will be 2 VDC by pi is the magnitude of the fundamental. It has a higher frequency, 3rd, 5th, 7th and 9th, so on, higher frequency components. magnitude of the square wave is VDC by 2. But then what is the input voltage? We had a center tap DC source with VDC by 2 and VDC by 2. So remember, input to the off bridge inverter is VDC, okay, but then output voltage is VDC by 2 in the positive half minus VDC by 2 in the negative half, okay. Input we have a VDC source, output it is VDC by 2 and VDC by 2, okay. So that's about off bridge inverter. More about it we will study in the next class. Thank you.